Okay, so last week we introduced, we talked about the number e and also the exponential function in the math module, but we realized that the one in the math module would not be able to help us do what we want to do, because with what we want to do, we want to produce a bunch of numbers, a lot of numbers. And for us to produce a lot of numbers, we cannot automatically produce those numbers one by one. So we need a way of producing numbers. We have found a form of the exponential function which works with what we want to do, which is going to accept a list of values and work out the exponents for each of those particular values, which is this one, np numpy.expo, then you give it something called an array. Okay, so what we need to do for us to produce these curves, which we need to do, we need a list, we need an array of wavelengths. Okay, from what I have in the notes, if I look at the lecture notes which I downloaded, Blackbody radiation, this curve seems to start from 0 all the way up to 5 here. That is 5 micrometers. So we want to produce a bunch of numbers. We don't know how many numbers we need to produce, but there is definitely a way of doing that. So up to 5 micrometers. So we can produce, create an array. So we can say create that's fine. Create numpy array what we are going to call wavelengths. You try to create this, an array which are going to call wavelengths. And the way we're going to create this wavelength, there are two ways we could do this. Saying np dot, the first one is to use something called arange. With this arange, we have a start value, and we can have a stop value, which is 5 e to the power minus 6, like this. So this, when you do that, it's going to produce an array of values like that. Then if you print this, what you're going to get is a bunch of values, a lot of values, which we can use. At the moment, you can't see that, but if we say print list, then this one, wavelength, what do we get? 0 to 0. Okay, let's include a step size. What is going to be our step size? 0.1. This is up to 5 to the power 6. So you could choose what? 1 e to the power, let's see. Well, let's try that. Let's see. If we did this, we have a bunch of values. The question is, how many values have you produced? So we could say length, what? Okay. So what we have here, with this function arange, we have produced with this function arange here, That the first one is the start value, the 0 is the start value. This other one, we're going all the way up to 5 times 10 to the power minus 6, which is 5 micrometers. Then we want this in steps of 1 times 10 to the power minus 9. And when you do that in these steps, we end up with these values. And how many are they? We see that we have produced 5,000 values. So these 5,000 values should be good enough for a plot. Are we clear?
Yes, sir.
Yeah, they should be good enough for a plot. So this A range, this is one of the functions which comes with NumPy, and we can use that to generate a list of values separate in steps of 1 times 10 to the power minus 9, since we're just going to 5 like that. Okay, so with this done, what can we do? You can carry out a bunch of computations with our wavelength. For example, you can do this lambda to the power 5. You can carry out such a computation. So you would for you to carry out such a computation, you'd say np dot power, then the variable the array wavelength. Come in. Then the power to which you want to raise to? Yes. So? I don't know any sound. What does it do?
He's an instructor.
Yeah, go and find him upstairs.
Upstairs?
Yeah.
But they told me I should come here.
I don't know. So here, as you can see, I've just carried out a computation which does, this is n to the power. So what am I raising the power? I'm saying wavelength to the power 5. So this is, so I'm doing done. So, so carry out, so compute, begin equation and equation. And equation inside here. What does this look like? Okay, so this is what I've just done here. I've done this. Wavelength raised to the power 5. And how did I do that? I said NP power, then the array I've generated, which is this wavelength, which has got 5,000 values separated in steps of 1 billion, raised to the power 5. So with this one, with this wavelength which you have, you can actually do calculations with it. Okay. The other kind of calculation, as you can see, you're trying to do is you're trying to do an exponent here. Exponent of b, then b, whatever b is, you multiply it by something, then this one, you raise whatever this is, b divided by lambda, which is again in an array, multiplied by t. So we will need a value of temperature to see if we can carry out this computation. One of the temperatures which we have is 7,000. So we're going to create a temperature variable, then give it a value of 7,000 and see how we could carry out that computation. So I'll do the following. So before that, I'll create variable temperature. Say creates variable temp, create a variable temp that stores 7,000. Like that. That's going to store 7,000 Kelvin temperature. Okay. So we're going to say temp goes to 7,000. This 7,000 comments. This is in kelvins. We do that. We can print the temp like that. So after having this temperature, we can actually multiply this temperature times the wavelength so that we can try to see if this actually works. We can work out this bit. This lambda multiplied by temperature. When you work out the lambda multiplied by the temperature, then we can try to see if we can carry out a division by B, because we already have a value of B. Okay, otherwise we have to find ways of doing that. So we're trying bits and pieces of the same. So this is going to be so lambda wavelength multiplied by temp. If we do that, what do we get? If we try to print, just try to print the wavelength times the temperature, what do we get? Does it work? So we are trying to multiply every value in wavelength with a value of temperature. So this is what we get. So it's actually something which actually works. So this wavelength can be multiplied by the temperature, where the wavelength is an array, then the temp is a number. So you can do that. You get something. Next, after you do this, so we're going to store this as what? So we'll need to store this as something. Let's just say wavelength temp is, so that's going to be wavelength times temp. So we'll try to store that as, oh sorry. Let's say creates variable the wavelength times temp. That's the wavelength temp bits. Then we'll try to see if, remember we have the A, so we have this bit. This we have now. This bit we have. Then we have got a value of B. Our value of B is this one. So let's try to see if we can divide B by wavelength temp. If it works, fine. If it doesn't work, then we have to find a solution of how to do that. So B divided by wavelength temp, so wavelength temp, then B. Try to do that. We run this, what happens? Okay, so there was a division by 0 encountered in this case. The reason why this division by 0 is because we started from 0. So where could we start from? Our array, instead of starting from 0, we could start from what? 1. What is it going to be? 1e. Let's see, 1e9. Something which is not 0. If we did that, okay, so if we start from a very low value, so just that was just for demonstrations, but I could choose even an smaller value where to start from. So this gives me what, 4,900. So I just lost one value, so I've got 4,999, and probably I could increase. $590. I think 4,000 is too fine. That's still a lot. You don't really have to increase anything, I think. Run this. We just want to confirm if in principle what you're doing works. Okay, so this seems to do something. Then next we say np.export. np.export. If we do np.export, then this B divided by wavelength. So we can say wavelength temp, B divided by wavelength temp. So we do a B divided by wavelength temp. We are trying to do this part. This B divided by wavelength temp, then later on -1. What do we get? Does it work? We run this. Okay, overflow encountered in exponential. Entry at launch point start. Infinity. So there seems to be a problem. If we choose to start from where? Let's say we choose to start from 2, power 6. 6. Let's this with 3000. 10. Okay, so if I start from 2 microamperes, 2 micrometers to 5 micrometers, we'll adjust this thing later on. We just want to see if we can find a way of making this thing work. So if we get this, next, this n exponential b minus wavelength temp, then we subtract it. We subtract minus 1 there. It gives us something. So the exponential of that minus 1 gives us something. Then at the end, remember we had np dot power, then wavelength, np dot power wavelength raised to the power 5. If we do that, then this multiplied by this bit, this multiplied by this bit gives us the denominator of our expression. That's now I'm not sure exactly why everything seems to be -1, but anyway, we can try to store whatever it is we have here. Let's see how it works. Do you know denominator? You can try to store that. Then we have a numerator. Numerator, which is, I think, A. Try to see in principle if what you're trying to do works. Yeah, so you A divided by that. So basically what you are trying to do is that divided by denominator. Later, this is going to give us our B. For now, let's just call it B. And let's see if we actually get something which makes sense. Print B. Okay, so we've got values of B. We also have values of, so this gives us values of B, and we also have values of wavelength. Like that. They should have the same size. If you say length of B, if you say length of B equals to length of wavelength, that should be true based on what we have done. So with this, we can try to make a plot of B against wavelength and see what we get. So if we make a plot, we're going to say imports matplotlib dot py dot pyplot as plt. So we do that. Then you're going to say plt dot plot the wavelength against B. Then plt dot show. Okay. So what do we have here? Not much to talk about. Negative 1.3, negative 1.3. So if we try to change our range, so in principle something works, but maybe our range is not correct. Try to change to 3. I'm just trying to work with a range which is from the sketch. Otherwise, we might have to find a better range. If the sketch thing does not seem to give us something useful. Yeah, we still don't get anything useful. And you have negatives. So what is the problem? Where are we missing something? Okay, let's search for Blackbody. Navigation. Okay. Okay, so the one we have here, saying here, if you can see my screen, there's one which is starting at 100 all the way up to 250 up to 2500, but if you look at the units, it's in nanometers, so maybe we also need to change the units we're using. So let's see if you can change the units we're using. Where is our wavelength? So hundreds. Here. I'll try to use something else. I'll try to do this. Lean space, linearly spaced values between 100 nanometers and 2500 nanometers, and I want 5000 values. I want 5000 values. I'll change that to this. So this one is going to give me from 100 nanometers to 2500 nanometers, and I want 5000 equally spaced values. When I do that, when I print that, it's a different approach. Okay, so those are the ones I have. And how many are they? About 5000. If I compute this, That's what I get. That's the temperature. Then I print it. Then I do this. Okay, then I do this. Then B divide by this. Alright. Then the expo bits. Okay, no problem. This one, no problem. Then that times that. Okay, and then that's our denominator. Then B divided by denominator. We print B. Okay, so those are the B values. We print wavelength. Then B equals to wavelength. Then we do the import. Then you try to print the graph. Still nothing. Right. Filter. Dots. Let me see. B values. Why is it not working? Yeah, exhaust. B against what B? Okay, so things are working. The graph can be drawn. The question is our values which seem to come out negative. And why? Because we are not supposed to have negative values. The negatives are coming from... Oh, sorry. So they're coming from here. So this is supposed to be the outside. Yeah, the negatives are coming from here. There. That bit is what's creating the negative bit. It's supposed to be that. So this should be done first. Then we print the denominator. Should not have negative values. Denominator. Print the denominator. Okay. I think. Get on. Like that. Wait a minute. That. Need better. That. Then delete this. When I was school, when drama. Then B. Okay. So it comes out. This is for the 7,000 temperature. So actually our thing comes out. So basically, as you can see, you can do some modifications by saying plot grid PLT. Are you seeing my screen?
Yes, sir.
You're following?
Yes, I'm following, sir.
Okay, so you can see the curve for 7,000 actually comes out. Okay, so based on these things, these rough steps we have done here, it means that we can create a function which is going to give us the values of which is going to give us the wavelengths and also the values of the same. In this case, I think there's a wavelength we are interested in, which is from 100 to 2,500, somewhere there. Okay, so yeah, we're also misled by the range which was in this, because it's supposed to be in nanometers. It's supposed to be nanometers there. Okay. So with this, the next thing we're going to do is we'll try to create a function. Since we know most of the things work, so we're going to say define, that is a spectral flux, whatever this thing is being called. Or we're going to say blackbody spectrum. Blackbody spectrum. So this function blackbody spectrum is going to accept a value of temperature. Okay, the range we will just do the range ourselves, but basically what we want is a value of temperature, as is per the our formula here. We just want to think for the value of temperature, then using the values of temperatures, once from here it accepts a temperature value. This range, we are going to create it inside the function. Okay, so after that, the next thing we do is, just before that, we're going to say a, the value of a. So we're going to copy the value of a because we need a. Where is a? We're trying to do a rough thing here. So we get an A. We also need a B. We need a B value. We need a B value. So we need an A value. We need a B value. Then after that, wherever this function is, we need to import numpy here. We need to import numpy. When we import numpy, we import numpy here. Then with the numerator, we set to A. Then the denominator, we after that we also create, after import numpy, we create wavelength. That's going to be np dot line space, we started with 100 e power minus 9 all the way up to, let's say, roughly 3000 e to the power minus 9 for 5000 values. So that's going to be a wavelength. So our denominator is going to be equals to np dot power multiplied by wavelength raised to the power 5 times some exponential function np dot expo. Then inside this expo, after that, minus 1. Then inside the expo, that's where we have the b divided by what do we have? Wavelength multiplied by the temperature. So we had that thing, wave temp. Remember? We created something called wave temp. Wavelength temp. So this wavelength temp is going to be equals to whatever the wavelength is. Wavelength is times the value of the temperature which we give this Blackbody function. So here we're going to have b divided by wavelength temp. So that should give us the denominator. Then after giving us the denominator, then the result is going to be equals to the numerator divided by the denominator for any temperature we're given. Then what we're going to give back is we're going to return two things. We want to give back the person the wavelength. Want to give back wavelength. We also want to give back result. Or what is it called? Power. Let's see. What was the B called? Yeah, emissivity power. So basically that's just the power, spectral emissivity power, emissive power, or we can say that Blackbody emissive power, spectral SP emissive power, spectral emissivity. Or we can just say, yeah, spectral something, spectral emissive power. We can do the whole thing, there's no problem. So this is what we want to give back the person. We want to give them the wavelength. We also want to give them the value of power. So we create this function. Yeah, Python is not complaining. So with this function, we're going to do a repeat of what we just did. So this time around, we're going to say Blackbody spectrum. We're going to say temp equals to 7,000. When temp is equals to 7,000, what you get is you get two arrays. You get this one, the first one, and the second one. The first one is the wavelength. The second one is this power thing here. So apart from doing that, we're going to repeat the same thing, but we're going to say wavelength. So we're going to use tuple unpacking, wavelength. Then we're going to say spectral power, spectral spectral emissive power. So that's going to be blackbody spectrum at temp, which is equals to 7,000. So this runs. So wavelength, when you check this here, wavelength, when you print it, wavelength has got values of wavelength. Print wavelength. That's got values of wavelength. When you print your spectral emissive power, it also has got that. But these are specifically for 7,000. Okay, so maybe we could have said spectral emissive power 7,000 K. So I think that's what's better if we do that. 7,000 K. So wavelength, that's that. Then spectral emissive power for 7,000 K. We do that. Did it finish? Need to work out things. So it will work out, then it will give us a result. Okay, calculation is done. There. What is this now? Supposed to be something there. What am I getting? Here it works. Then here it says it's not defined. Why? Interesting. So did this thing work? Okay, there it is. So now with these two values we have returned, we can use these to make a plot. You can say plot dot show PHY dot plot, then wavelength, then the other one is a spectral business, this one for 7,000. So that's a key for 7,000. Okay, you can give it a label. You say label, then inside there you say 7,000 RIM kelvins. Then after that, you say PLT dot legend, then PLT dot show. So there, that is a 7,000 Kelvin scale. Then other things you can add, say PLT dot X label. X label is the wavelength. Say wavelength, wavelength. You can put some dollar signs. Lambda in units of nanometers. Do that. What do you get? Yeah, so there you got wavelength lambda in units of nanometers. Then on the X label, PLT dot Y label, you have your spectral emissive power B the function of lambda in terms of T. So when you do that, okay, so this is what we get. So basically maybe it's just even better we just do B. Just do B. The A we just do lambda. B and lambda. There. So we've got wavelength here in nanometers. Then your spectral thing that side. You can also add a grid if you don't mind. You can add a grid, PLT dot grid. Then just move this one, I think, a bit down. So the function we have written, the Blackbody spectrum function you have written actually works. And the arrays we get from that particular function, we're using those arrays to make plots like this. So this is a plot, the curve for 7,000 kelvins. The other temperatures which we have been asked to use, are we clear up to this point?
Yes, sir.
Yes, the other curves we have been asked to make are for temperatures 5,800 and 3,000 kelvins. So we're going to do something similar for those caves also, but now we're just going to combine everything. Okay. All the caves,
Yes, sir.
yeah, we're going to put them in one place. So we're going to copy this particular one here. We're going to copy this line. So we're going to call this function twice. First one with the temperature of 5,800. We already have the 7,001, 5,800, so we don't have to do that anymore. 5,800, so we're going to call this one 5,800. 5,800. Then we're also going to call the same function with 300 kelvins. So we produced data for 300 and also for 5,000. So we'll run this one first. Then the values of the wavelength are still the same, so that doesn't really matter so much to us. So now we have spectral emissivity power for 5,000, spectral emissivity power for 300, and yeah, so we're going to copy this guy. copy this. So we're going to make different plots. Control plus A, copy. So the first one was for 5,000 something. Then we need another one.
5,008.
Yes. So we need for 5,008. 5,008. And you're going to call it 5,008 side. 5,008. And we need another one for 300. 300. Which we're going to call 300. So, hopefully, now the magic is going to happen. And you're going to have our 3 graphs on the same plot. And that's what you see here. So we have our 5,000, our 7,000 there, all the way down there. Then we have our 5,800, the orange one there. Then you have got our 300, which is almost flat. So what I suspect we need to, so we have our 3 graphs there. We can add a title to this thing. You can say POT dot plot title. Then we say Blackbody spectrum. Blackbody spectrum. So when you enter title, this thing, this is what we have. So I think maybe the range is too much, up to 3,000 something, because we're just using an example from what we've picked. So maybe we can go to 2,500 or 2,000, or 2,000, so that you can see clearly. 2,000, I think. 2,000 could help. 2,000 could help us. So for us to do that, where you change the range, you go into the function here, because we went up to 3,000, right? So now we go up to 2,000 there.
Yes, sir.
Then between these we produce 5,000 points. So we're going to rerun our function, our Blackbody spectrum function. Then after running our function, now we are going to also probably copy this line, put it together with the other lines. Going to put it there. So we'll run them at the same time. So this one, first one runs, the second one runs, okay. So the 7,000 one has run, 5,050 has run, then the 300 one Kelvins has run. Then we make a plot. Okay, but it's still not very evident.
I think maybe changing the temperature, sir.
Sorry?
I'm saying maybe changing the temperature to 3,000. That one for 300.
No. The exercise says 300. That's what we asked. We asked to find the curves for 7,000, for 5,000 that, then 300. Okay, we can do an experiment, change it to 3,000 and see what happens if it's actually just the temperature itself or something else. Yes, we can do that. Okay, so let's change and see what happens. So here, if we change to 3,000, we see That's in the plotting, but you also need to change it 3000 here and there. We can also make the individual plots. I think so. We can do the individual plots for each and see if it was actually working. And because the effect you're seeing is the effect of all the plots being put in the same graph. Okay, that's why the other one, I think, looks like there's nothing happening there. So you can see it has moved a bit. So I think let us just leave it at that, but we're going to plot. The other thing we're going to do, after every one of these, we're going to make a separate plot, an individual plot. Okay, so we're going to do this, then that. So here we just make the plot for 7000 so that we see if it works, and what we are observing is just the effect of putting things together. Okay, so that is for 7000. Then we add space. Plot. Okay, this. So this is a 5500 plot, right? Yeah. So we'll check the 3000 plot, the 300 plot, what it looks like, so that we can convince ourselves that the flat line we are seeing might not actually be a flat line, but it is as a result of more powerful caves, or caves with very large amplitude being put together with it. You see? So that is the 300 cave. Okay? Hello? All right. So it looks like we are correct. So we'll go back to our spectrum. We'll adjust our thingy to, let's say, 3000. Yeah, I'll make the adjustment to 3000. So run that. Then after that, we'll work this at 7000. Then you make the plot. So this is 7000 plot. Okay, at 7000, that's a plot. Then at 5000, then this is a plot, 5000 kelvins. Then do this at 300 kelvins. That is a Blackbody cave at 300 kelvins. Then when you put them together, there they are. So you've got the 7000, you've got the 5500, and you've got the 300 Kelvin Blackbody curve. These curves can be saved to a file. So you copy this. I think you say After show. Which one is it? Is it after show or what? POT T dot Safig. Then we say Blackbody spectrum dot JPG. I think it's supposed to be inside. Let's see how it works. Okay. Has anything been saved? I can check on my drive. So maybe one of two, either this one. Not sure if that has produced anything, but I can check on my drive. UNZA drive. That's then column. Has it produced anything? Drive. Yeah, I'm trying to see if I can save. I don't know, because one of them works. I'm trying to save this graph to a file, and I'm trying to show how that's done. So one of them works. I'm not sure exactly which way, whether the save figure comes before or after the show. But yeah, I'll try to see if I can find a solution to that. Okay, I don't have anything. If I do the following, but the point I'm trying to show here is that these caves can actually be saved to a file. That's, if I put it after, what happens? Okay, something has happened. Do you have anything? But I can't see stuff here, that's the thing. Anyway, any questions on the on how to exactly save this thing to a file? I think one of the notebooks, the one on data visualization using MATLAB, using Matplotlib, it shows you exactly how you can save your thing. Anyway, let me see if I can open it. UNZA Moodle, just a minute. We're almost, I think we are almost done. The next part is, so we have produced the graphs, you have put them in the same plot. The next part is how do you do the integration? Okay, because remember you asked to find the area under the graphs. That involves integration. So how do you do the integrations? So that's what we're going to look at next. I think we're supposed to meet next week, but I have some commitments, so I highly doubt I'm going to meet you guys next week. But let's see.
Okay, sir.
Yeah, let's just see. Here, data visualization. So open this. Then that's what you're supposed to use these things for, to check how to do something. Okay, if you need to make a plot, how do you make a plot? So what do you need? And stuff like that. So I want to see where you save a figure to file. Closing windows, not non-interactive scripts, this error bars. Where is saving the file? There should be something on 75. Okay, that's the end. So we need to go up a bit, I think. Error bars, and interactive reporting, clear the diagram. Okay, so the save fig should come before, I think. I've seen save fig here. I think it should come before it. Before show. Let's see. Yeah, saving the save figure is used to save the current thing. I think save figure should come before you show. This. So after this, most of the time you at the end you put show. So I think that's where it's supposed to come. So I think the correct way is supposed to be this one, where you put it like this. So plt.save figure, then how you want to save the file, spectrum.jpg, then you say show. So we can get rid of these. Are we clear? Are we clear with what we've done? Okay, so
Yes, sir.
I am going to, as usual, I'm going to upload this video to YouTube, then share it in your thing, but I'll also make extra effort to share this notebook, okay? So that you see how you're,
Yes,
yeah, then from this notebook, you should be able to extract what you need to answer our lab, okay? You should not give me back the lab the way I have done things, because me, I was experimenting. Okay. Now that you have a good idea of what you're supposed to do, you pick the lines you need for you to produce your graphs, then you give me. Okay.
Yes, sir.
Yeah. So we'll come to an end here. The other bit of integration will continue when we meet. I think maybe we might meet next week, but I'm not promising next week very much. Maybe that other week. Okay. So in the meantime, continue studying on, study how to make plots. Then also study NumPy. As you can see, we have used a lot of NumPy today. So study NumPy, study how to make plots. I also added a thing on numerical integration, SciPy, so that you go and have a look at it and see how you do numerical integration. That should be chapter what? That should be 17. This is 16. I think I added something on 17. Chapter 17 here. 17a, Introduction to Numerical Integration. This is what we were supposed to do when we were doing our computational physics. When you're doing numerical integration, how we're supposed to do it, but we did not have time, so we only ended up kind of doing things only the hard way. But here, if you go through this module, it shows you how using Python you could do your trapezium or your Simpson and the other integration methods. So here integration using SciPy.integrate, then you do that. Then how you use composite trapezoid rule. Then also how you would how you do things with, I think there should be Simpson, how you do your integration. here Simpson's method, how you carry out that integration. Then what's this? How you do this rhombic integration, and also how you do another kind of integration called quadrature integration. So basically there are 4 types of integrations which you could do using Python, and they should be able to save all your purposes as far as integrating is concerned, like this. So please have a look at this also. It's going to help you a lot. Okay, we are not very interested in doing things the hard way.
Sir.
Yeah, we want to find, since we spent so much time learning about Python, we want to find how to use it, and let us use it to the best of our abilities. Okay, so we end here. Yeah, next week we're definitely not meeting. Maybe that other week, but I'll keep you posted, and I'll keep on posting things on your on our Python thing for the course. Okay, so I'll see you, and have a good weekend.
Okay.
Yes.
You too. Thank you, sir.
You're welcome.